Welcome to lesson 32. So now we're going to look at the ANOVA table and sums of squares. Just so you know, this is one of our fun things. For us anyway, we love to give partial ANOVA tables and have people fill in the rest. The relationships help us build together like what the mean square for the treatments and error are, and then get our F statistic. So here is a standard ANOVA table. So sum of squares for treatments, we sum over the groups, and we're looking at how different the sample mean for one particular group is from the overall mean. Sum of squares error is saying, okay, well, how much groups variability? It's a weighted average. Are we seeing over all of the, like within the groups? And then total is just saying, hey, if I went ahead and mapped an overall mean, how much does each observation differ from that overall mean? And you can calculate, okay, there's this much variability. This much of it's explained by the treatment. This much of it's explained by unexplained. So it's error. We then have degrees of freedom. So we have degrees of freedom for the treatment. So number of groups minus 1. Degrees of freedom for the error. So n total minus 1, and degrees of freedom total, so just your total sample size minus 1. And things to note, like this is why I was saying be very careful, make sure you write a T with a little r for treatment, because SS total will just be a T. So then we have our mean square treatment over our mean square error, that gives us our F statistic. And the p-value is just going to be this F statistic on degrees freedom of treatment and degrees of freedom error. This is my numerator, degrees of freedom, denominator, degrees of freedom, the area in the upper tail. That'll be our p-value. So absolutely, if we give you the first two columns here, we've given you more than enough to complete the rest of the table. We also really love to play games where we're like, oh, we'll give you this one, this one, and this one. That's also enough information. So we really love doing that. So this is my ANOVA table for the example that we used in lesson 31. So we're looking at we have groups of 5 carbon materials, and we have them each at 4 different temperature treatments. So 300, 400, 500, and 600 degrees Celsius. And we want to see, on average, does the average pore size differ for at least one of those treatment groups? So temp factor, this is my factor here. This is my degrees of freedom for my treatment. This is my degrees of freedom for my error. It gives me my sum of squares, so SS, mean square, MS. So if you can get on board with this is my treatment, and this is error. When you see residuals, that tends to be synonymous with error for us. So then from there you just line up. Sum of squares treatment, this is sum of squares treatment. Sum of squares error, SSE, and so on. There's my F statistic. It's rounded a little bit. You can actually pull it out and it'll give you more digits if you want. And then there's that p-value as well. So our results here shouldn't be different from what we calculated before. But we have, using the 0.05 significance level, because it says right here, I'm going to say, oh, my F statistic was 12.1 with 3 numerator degrees of freedom and 16 denominator degrees of freedom. P-value equal to 0.000219. Once again, always round these to at least 2, if not 4 places past the decimal. Especially p-values, we do not like it. Like WebAssign is okay if you round that, if you round to 0, but we won't be. We have a tendency, like if I had 0.000001, in stats, most of the time we would just say our p-value is less than 0.0001. We do not like to round down to 0 because a probability of 0 means something's literally impossible. We don't like it. We hate it. So, caution. So here we have my small p-value, my bigger significance level we're going to reject, and then we would fill out the rest from there. So there is, it's pretty strong. So very strong or convincing evidence that at least one of those means, so the mean pore size, of carbon materials. And if you just watched lesson 31 with me, you'll notice this is pretty much identical to that last slide that we just filled out. Differs for at least one of the 4 temperature treatments. Oops. And I'm a fan of writing them out. That way we know what they are. Because it really stinks to look back at something and read and you're like, hey, what were those treatments? I don't know. To actually forget the context and not be able to even remember like what this is tied to makes it very, very difficult. So that would be my write-up there for single factor ANOVA. Looking at my sum of squares here. Here's my table again. So what's really cool is you can break the sum of squares into parts. So you have your sum of squares total. So this is all the variability that could possibly be explained or not explained. This is how much is explained by like the means here. This is how much is left over. So if you look here, you add down 1 plus 2 is equal to 3. That kind of thing. So my sum of squares for my treatment plus my sum of squares for my error will be my sum of squares total. It works for the degrees of freedom also. So 1 plus 2 is equal to 3. So that's really cool. And then when you go across, it's not going to add across. You're going to divide. So this divided by this is that. This divided by this is that. We do not fill in these two squares. We don't find mean square error. Well, total. We don't find mean square total. It's not necessarily meaningful here. So we're going to stick with mean squares for your treatment. So the sum of squares, so what variability is explained by the treatment divided by how many degrees of freedom your treatment has. So it averages them. Hence the mean squares versus the variability within your groups divided by the number of degrees of freedom for within your groups. It's going to be your mean square error. So now we're going to go ahead, we're going to compare here. We're going to look at between and within group variability for each plot. And this is SSTR. Sorry, I used G before for groups. And if you see G anywhere, just know that I was using it for treatment. Know that WebAssign will use TR for each of these. So how do they compare? So here, this is a giveaway, equal means. Right? So we know that they have equal means. And not only that is they have equal variability. It's A and B and C, they're all the same. So you end up getting an F statistic of 0 because they're identical to one another. So these means are exactly the same. So are exactly the same. Sorry about this. It takes me a little bit longer to write and talk at the same time. Exactly the same. So the in between group variation groups. So we're talking about MSE is 0. So we're going to fail to reject the null. So the null being that all three means are exactly the same, we're definitely going to fail to reject that here. Because, I mean, not only are they close, they're identical. So we're definitely not going to find that they're different. So then, scenario 2, here we're looking at they have the same variability across groups. I mean, like within each group. So the variability of group A is the same as the variability of group B, which is the same as the variability in group C. However, you can see that they're not all the same mean, right? They have different means. So the means differ. The between group variation increases from scenario 1. In particular, the further apart the group means are, the more that'll increase. The within group, so looking at the variability within each group, group is same across groups. So if you're looking at the 0.05 significance level, we are going to reject the null. We're going to conclude at least one of the means between A, B, and C is different than the others. At least one. And then, unequal means. So not only are these means not equal, the variability within each group has become a lot smaller. So means are different. So means differ. Same means as in 2. But the within group is now smaller. Within group variability is smaller. So now what this is saying is most of the variability is between the groups, not between and within. It's mostly between the groups. So we're going to have even stronger evidence. Look at that F statistic. It went from 3.8 to 66.74, and that p-value is tiny. We're going to reject. And just a reminder, see how small this p-value is? We don't expect you to necessarily write out something that small. It would be okay to say, okay, well, p-value is less than 0.001 or 0.000. Oh, basically, we like 0.001 or 0.000. Too many zeros. 0.01. So 1 in 1,000 or 1 in 10,000. That's what we prefer. Just tell us the p-value is smaller than that. That tells us enough. It tells us it's small and it's smaller than this small number. So that'll be enough there. So which of the following here are false? So we're looking at a side-by-side box plot. So you might notice this is not a horizontal box plot. So looking here, group B and C are similar. Looking here, those boxes have a lot of overlap. Those medians are really close. Heck, even the spread looks really, really similar. I would say this is true. So since this is asking what's false, A is not going to be what's false. A looks very true to me. Group A seems to have lower values than the others. So if you look at group A, yeah, absolutely it does have lower values. because it's ascending this way. It goes from anywhere from under 20 to maybe around 50. All the others are like, I don't know, at least 45 and higher. So this is also true. And then here, this last one, the greatest difference is between group A and B. They definitely do have a notable difference here, but I would argue that A and D have a bigger difference than A and B do. So this is the one that's false. I would say C is false because A and D have the greatest difference that we observed, not A and B. And then one more. So which of the following statements is false according to our output here? So remember, this is my, this is my treatment. I believe it's the, is it temp? No, it's not the temp. It's just treatment. And then this is my error. So E, and this is TR. If it's helpful for you to relabel those, that's great. Just note residuals, that goes with error. T is generic, so we put with treatment. It'll honestly be whatever your factor name is, that's what your treatment there is. So the estimate for average variability between the groups is 4,165. So between the groups, I'm looking at treatment. No, this is true. So it's talking about specifically MS treatment. That's true. So there is no evidence that at least two group means differ. So looking here, I have an F statistic of 20.58. So if my degrees of freedom are anything, on numerator degrees of freedom 3, denominator degrees of freedom 44, and a p-value, look at that, that's really tiny. P-value less than 0.0001. That's a small p-value. In fact, that p-value is going to motivate me to reject. I would say there's very strong evidence at least one group mean differs. So I would say B is false. This is not true. And then just to check, the F statistic comes from an F distribution with 3 and 44 degrees of freedom. Yes, there it is. It's right there. So this is also true. So sometimes we have questions structured like that, like which of these are false. That means 2 of them will be true and 1 will be false, and we want you to pick the false one. So that should be, okay. One more, so the analysis of variance procedure, we want you to think of it as a 2-step process. So the steps that we have been doing up to now is we ask, hey, is at least one of the means different? But tell you what, you go ahead, you get hired by a client and you say, yup. Well, they're going to get very annoyed with you very quickly if you don't tell them which means are different. So if you decide at least one is different, so if yes, move to step 2, then you just want to determine which groups are different. So we have multiple comparison method that we're going to use in the next lesson. That's what's coming up next. So yes, first you ask, hey, is at least one different? If you say no, you're good. You stay there. You're like, okay, I don't have evidence that at least one mean is different than the others. You're not going to try to find which ones are different if you say none of them are different. But if you do say at least one's different, then we want to figure out which ones are different. So lesson 33, coming up next, multiple comparison procedure for means. Specifically, we're going to go into Tukey's method.